when you're asked to find the area of this shaded region here, everybody knows that okay. You see what's happening right now, right? There we go. Everybody knows it's the integral from -2 to 3 of that function. Okay? Keep in mind what we're really doing. Gentlemen, I know you're working together. You gotta be quieter. You're distracting me. I'm easily distracted. What is that? Okay. Hello. What's happening? Thank you. Lauren, Benjamin. Is Lauren here? Is Benjamin here? Huh? Okay. Sorry, I'll keep her. All right. Yo, let's just make sure everybody understands what we're really doing here, okay? We're really putting these rectangles. Oh, man, I'm having trouble. What are you doing? We're putting these rectangles in here like this. Now, I'm drawing them, but they're all really infinitely thin. Y'all with me on this? Yes. Okay. And if I put in all those rectangles, add them all up the whole way across the shape, that's going to add up to the area, right? Okay. What's the thickness of each one of those rectangles?
Infinitely small.
Infinitely thin. It's an infinitely thin change in what variable?
X.
So what do we call that?
Dx.
Dx. So the area of every single one of those rectangles is dx. Yeah? What's the height of every single one of those rectangles? The y value, okay? But this computer's messing up. But I can't put a y. So you're right. Technically, it's y times dx. But we can't have a y and a dx. If dx is our infinitely thin thing, then we need everything in x's. What's y equal everywhere? X squared plus 4. So all we're doing is taking a height and a width and multiplying them together. That's the area of one rectangle. Yeah? And all we want to do is add them all up. So we use a big S, which stands for sum, right? But it's still an integral. And we say, hey, add up all these rectangles from -2 to 3. And that's what that does. And we can do it on a calculator, and we get, what do we got? I forget. 32? 31? Thank you. 0.6666. Oh my gosh. And we need to be 3 places accurate, okay? Now, here's what I'm telling you. We can't really put infinitely many rectangles into this thing, all right? But here is the basic idea. If I were to go ahead and manually, like physically do this, put 100 rectangles under here, right? See them all drawn there? And add up the area of all of them, I should get an answer close to 31.667. True? Let's say I got 31.5. Okay? And then Laura comes along and says 100's not enough. I'm going to put 10,000 rectangles in there. And if she does it, she might get 31.6. Makes sense? And then David comes along and says, get out of the way. I'm going to put 1,000,000 rectangles under there. He's going to get like 31.66. Okay? And what's happening is the more rectangles we put in there, the closer the area gets to the actual area. And that's what the integral is. It's the limit of putting more and more and more rectangles in there. All right? That's what's really going on. When we do it over here for this function, the same thing's happening. But now we're integrating from 0 to 2 pi. Okay, now this is going to matter because we're going to start changing up and getting some weird shapes. Okay? I forget what that was, 18 something? It was right here. 18.85, basically, if you round it. Okay, and again, that's infinitely many rectangles under the curve down to 0. Okay? So, let me throw a question at you. Let's say, well, before we get to that, if I made a number line, a vertical number line like that, okay, and I told you 12 was here and 3 was here, and I asked you how far apart those were. How far apart are they? 9, right? 12 minus 3, top minus bottom, big minus small. What if instead of that being 12, it was A and that was B? Now how far apart are they? A minus B, whatever they happen to be. What if this top was like some function that was changing and this bottom was some function changing? Now it's f of x minus g of x. Make sense? So, keep that in mind. If we want to find the area between, I don't know, let's go, oh, let's do one more over here. Even if these are negative, because sometimes kids get messed up with negatives. Let's say this is -12 and this is -21. How far apart are they? See the negatives, like what? They're not negative 9 apart. They're 9 apart. Okay? Do you see that we are doing negative 12 minus negative 21, right? It doesn't matter if they're negative. We're still doing the top minus the bottom. Okay? So if I were to graph, let's make this look a little bit nicer. X squared minus 4, which is this function here. And I also gave you the function. Gee, what is going on? G of x equals x plus 2. That's going to look like this. What if I want the area between those curves? Do you see how they close off an area? So on the AP test, I like to ask questions like this. Hey, what's the area between these curves? It has to be a closed, defined area. All right? Let me switch up my colors here. So good. Boom. Doesn't make sense. That all we're really going to do is put rectangles in like this and add them all up. Again, there should be all the way over here to the end. I'm not going to draw them all, but that's basically it. Make sense? What's the thickness of every single one of those rectangles? Infinitely small. What do we call it? dx. The height of every, no matter where I draw these rectangles, what's the height of every one of them? F of x minus g of x, which is x squared minus 4 minus x plus 2. Look how I have to write this. X squared minus 4 minus x plus 2. And then all I got to tell this thing is, where do I want my rectangles to start and where do I want them to stop? So what do I need to find? Where they intersect each other. Yeah? Do you remember how to find where things intersect? If we had to do it by hand, what do we do with those functions? Set them equal to each other and solve it. A lot of times you're going to have a calculator. We don't need a calculator for this. This one's going to work out. This is how you find those intersections. Okay, so if you have to do it by hand, you do it like this. You're going to bring that x over. Bring the 2 over. You get that? That factors. X minus 3, x plus 2. So they intersect when x is 3 and when x is negative 2. You see that happening. Here's 3. Here's negative 2. So we want to add up all those rectangles. Yes? It would give you, like, so it has to be between things. So if they want the area below the parabola, they'd give a function down there somewhere. Okay. Everybody get the hang of this? Yeah. So just like I was showing you with that number line, the vertical number line, it's always the top minus the bottom. Big minus small, because you want it to be a positive value. So if you look at this right up, the y value here could be, I don't know, like 1. That makes sense? And the y value here could be like negative 3. So that whole distance right there is 1 minus negative 3. 4. God darn it. Yes. Why do I say that to me? Maybe we look stupid up here. We're subtracting the wrong way. We're subtracting the wrong way. The video is ruined. Come on, David. I'm just on autopilot up here. Yo, it's the line up top here, which is x plus 2 minus the parabola. Cool. Thank you, Laura. Plus 1,000,000 points to Team Laura. Yeah, that was bad. Yo, what's the difference between the first way I had it and the second way I have it now? The answer is going to be what? Yeah, one's going to be negative, one's going to be positive, right? We want the positive value of this. Okay? Yeah, I know over here it looks like G is on the bottom, which is a visual thing, but it matters what's on the bottom, what's on top when you're actually drawing your rectangles. Everybody okay? So we can put that in a calculator and get an answer. I'm going to forego that and give you another question. Can you find the area between f of x equals cosine x and g of x equals, what's something good? Excellent. x squared minus, I don't know, let's put this over there, 2x minus 3. Need a calculator for this one. So first thing we want is a nice picture of what this looks like. So we graph it. Okay? A lot of times in the AP test, they give you a picture of it. Cosine looks like that. And x squared minus 3. What's wrong? It's a spider. Okay. Has to look something like, what's that factor into? Minus 3 plus 1. So it's going to hit a negative 1 and a 3. So something like this. And again, we're going to graph it anyway, but I'm just showing you. A lot of times they give you a picture of what it looks like. So the shape we want is right there. On a calculator, since we're going to have to graph it anyway, I'm going to graph cosine x, and I'm going to graph the other function, x squared minus 2x minus 3. When I graph that, I'm going to set my window just to be a little bit nicer. I'm going to do like negative 3 to 4, count by ones, and maybe negative 5, that'll work out, to 4 to 3, that'll be good. There's that super cool cosine graph. So here's the picture, looks something along these lines. We get that? So what's the area of each one of these rectangles? We got what's the thickness when we draw them? We're making them infinitely thin like this. That's right. The thickness is dx. Good call. And what's the height of each one? What's on top of those rectangles? Cosine of x, yeah, okay. And look, no matter where you draw these rectangles in this shape, what's always on top? Cosine. That's what matters, okay? It matters what's on top the whole time. If the top changes, we got to do something different, okay? But the top is cosine, and the bottom is x squared minus 2x minus 3. Only thing we got to find is, where do we integrate from where to where? So on a calculator, to make sure we can all do this, you're going to hit second trace. That's to get to the calculation section. And we want to find the intersect. That's 5. And all it asks for is what's the first curve, what's the second curve. If you only have 2 curves drawn, just hit enter. It chooses the first one. Enter again, chooses the second one. And then since there's 2 intersections, you got to either move the cursor close to the one you want or just type in the x value that's close to it. I can see they intersect close to negative 1. So to find that one, I'm going to guess negative 1. Calculator will do its little algorithm, and it finds it. Okay? I don't want to have to write that number over and over and over again. Sometimes you have to use these numbers multiple times. So all I'm going to do is quit out of here, second mode, and I'm going to hit store alpha A. And that puts A as that number. Remember we did this for the rate in, rate out problems. Okay? I'm going to write that on my paper. You hit store, which is right above on. 10854. And then choose a letter. 5444. Okay. Now in this case, it really doesn't matter because we're only going to use it one time. But if you have to do more than once, doing this saves you a little bit of time. You have to keep writing it. And storing it means you're not going to mess up typing it in. Everybody okay with that? We're going to find the other one. I'm going to call it B. And I'm going to integrate the B. So I'm going to go back to my graph. We're going to hit second, trace, 5. First curve, second curve. It looks like it's around 3. Enter. And it finds it 2.7533. I'm going to quit out of there and hit store alpha B. And that saves that. So 2.75339 and some change. 8394. Everybody good? As long as you write them on your paper one time somewhere, if it's a free response question, you can keep using A and B all the whole time. Yes? What do you mean? Yeah. Yeah, you need to integrate from left to right. So A has to be the left one. The way I have it set up, yeah. This we have, no matter what you call this point right here, we're going to start from that point. Otherwise, you're going backwards, and it's going to spit out a negative. It's going to spit out the opposite of the answer. Remember, integrating backwards is the opposite of what you would have got. In your calculator, you're going to hit Math 9. You're going to say, hey, go from A to B, just alpha A, alpha B. And I like using y1 and y2. I put cosine into y1, put my other function into y2. The benefit of that is, a lot of times, students will forget to put parentheses around their functions, and then the negative doesn't distribute, you're going to get a different answer even though you did everything correctly. So you put in y1 and y2, you don't have to worry about that. All right? And then dx. And if you're playing along, you should get 32.489. Okay with that? Excellent. So, that's area. Let me show you some weird things that could happen. Okay? Let's say we wanted to find the area between, what's up? Or underneath. Let me think of what are some good functions we can use here. So, let's find the area of the region between. Did I mess up? Why? Did I not put in my functions y1, y2? I did. Man, oh man, I'm falling apart. Oh, I multiplied it by x. Darn it. So if I divide that by x, is it that? Okay. Man, this is the worst video ever. 799. Well, 7. Well, basically 0.8 if you round that, right? Okay. All 3 people who watch us are going to be like, Mr. Smith, come on. All right. But you get the gist of it, right? Regardless of me messing things up. Okay. Let's say we have y equals, or f of x equals negative 2. Let's also say we have, let me think here, g of x equals, it's a good one for us to do easily here, ln of x. And let's say we have h of x equals 5 minus x. Okay, so before we graph it, on our calculator, look, you guys should kind of know what these functions look like in general. Let's think about this. F of x equals negative 2 is a horizontal line at negative 2 down here. Okay with that? Ln of x is a function that comes up like this. Remember where it hits the x-axis at 1. That doesn't really matter for this question, but that's what that is. Remember, we graph ln of x all the time. Okay? And 5 minus x is a line that has a y-intercept of 5 and a slope of negative 1. Do you see the area that they close off? Okay? Let's just draw that in blue. We have this here. We have this side here. We have this side here. Okay? So, what's a little bit different about this one is this, and I always recommend you draw your pictures here. Okay? If you draw rectangles in this shape that are vertical, check this out over here. Let's say we drew one right here. If I draw them all over here, what's the top of every single one of these rectangles? Ln of x. And what's the bottom? Negative 2. So the area of those rectangles is ln of x minus negative 2 times dx. And I need to integrate them from where I start to where I stop. But look what happens in the middle. And this is something you always got to check. What happens once I cross this point? Now these rectangles are defined by what function on top? 5 minus x. And the bottom is still negative 2. Does that make sense? So what we're really doing there is kind of finding the area of two different shapes that are just touching each other, which means we need two integrals. The first integral is going to go, I'm going to say this point where they hit right here is A. I'm going to say the point where they intersect is B. I got to find that. And I'm going to say the point where the line hits over here is C, and we can find that pretty easily too. So my rectangles are ln of x minus negative 2 between A and B. So that's what I'm going to do. Is everyone okay with that idea right there? That finds this area here. And because the top changes in the middle of the region, I need other integrals. I need another integral. So to that integral, I'm going to add, I'm going to write it down here, plus, now my rectangles are 5 minus x minus negative 2 dx. Okay? And we're going to add those all up from B to C. So all I got to do is find what A, B, and C are. Any questions so far? Feeling good? This happened specifically because the top changed. If the top or the bottom change at all, you need another integral because it's a different shape. The rectangles are defined by different bounds.
Wait, every time you have to always make them equal another integral?
If the top or the bottom changes, yep. Okay? So just to put this into a calculator, well, first we got to find them. So let's graph ln. Let's graph 5 minus x. Delete the rest of this junk. Ugh. That's not what I want to do. And let's graph negative 2. Oh, we're not going to be able to see the other. I got to change my window. Okay. Got to make my x max bigger so I can see what's going on. We're going to go out to 10. By the way, this happened second period. Do you see how that blue curve there, which is ln of x, kind of stops? ln doesn't really stop. It's just a calculator has trouble calculating those values, so it just stops graphing it, which is weird. Okay, the ln goes down forever. But we need these intersections, so you got to be careful about this. Second trace, 5. Initially, I'm on the first curve, enter. And then it puts me on the red curve. I don't want to be on the red curve. I want to be on the black curve. And I'm going to guess 0.5. And we get 0.13533. Is that okay? I'm going to store that as A. I would write that on my paper, A equals. So I'm just going to quit out of here. Hit store, alpha, A. Boom. Okay? I'm going to go back to my graph. I'm going to hit second trace, 5. I want the intersection between the blue curve and the red curve now. Okay. Here's the blue curve. There's the red curve. Enter. And it looks like it's around, what, 4 maybe? And we get 3.693. I'm going to save that as B. I'm going to quit. Hit store, alpha, B. There we go. I'm going to find the other one. The other one's easy to find, though. Where's 5 minus x equal negative 2? Well, x is 7. Yeah, okay. So C is just really 7. So I might just put 7 in there rather than have to deal with that. And that's what we're going to do. And just to make sure we can all get the same answer and Mr. Smith can get one right for once, I'm going to go math 9. I'm going to integrate from alpha A to alpha B. And I'm going to do ln of x plus 2, which is minus negative 2 dx, plus math 9. I'm going to go from B to C, which is really 7. And I'm going to do 5 minus x plus 2. And I put in 2. See, the problem is, it's this computer. My pen is double hidden buttons. It's not my fault. Kablow. Did we get 14.121? Yes. Okay. Equals 14.121. Feeling good? Last thing I want to show you. Ready? just like we're putting in vertical rectangles, sometimes it's easier to put in horizontal rectangles.
No way.
Oh, yeah. With area, you don't have to do this. Vertical rectangles can always work, but when we start talking about volume, sometimes you're going to have to use horizontal situations, okay? I know, right? So, let's discuss. Let's look at that same exact area. We had ln of x coming up like this. We had 5 minus x coming down like that. And we had x equals -2. So that's our area, right? The axis happens to be in the middle of that, but the axis does not matter at all. Don't worry about the axis being there. It just happens to be there in the shape, okay? This is where it lives. Instead of putting my rectangles up and down, which just worked, okay? It worked out fine. Doesn't make sense that I could also, if I was feeling crazy, put rectangles this way. And if I put a whole bunch of rectangles in here, do you see how that would add up to the area that's in here? If I put in a whole bunch of them? Okay? So, by the same exact idea now, all I got to do is find the length times the width and add them all up. But which variable am I crushing down right now? What's the height of every single one of these if I put infinitely many of them in there? Not dx, dy. We're crushing down the y value. The height of every single one of these is dy because it's infinitely thin slices of y. Okay? And now, think about a number line that goes like this. Forget that graph for a second. If I said this is 24 and this is 11, and I asked you how far apart are these, you would tell me 13 because you're doing 24 minus 11. So if I asked how far, what's the width of these rectangles, we have to do the right side minus the left side. Does that make sense? And there's one extra small change. The variable I'm integrating with respect to is y. Okay? So you cannot, now remember this curve over here is 5 minus x, and this curve over here is ln of x. So a very common mistake kids will make is to say, oh, it's 5 minus x minus ln of x. Okay? That's not what it is. This equals y here. We have to solve that for x. I need x equals with a y in there. Okay? Because dy at the end of my integral. It's not hard to do. This is just x equals 5 minus y. Is that okay? And the other one, ln of x equals y, is the same thing as x equals e to the y. Is that okay? So the width of those rectangles is 5 minus y minus e to the y. Okay? We're still subtracting the curves, but it's the right minus the left now, and we have to do it in terms of y. So this is 5 minus y minus e to the y dy. That's the area of one of them. Do you see that? Look, no matter where I draw these rectangles, what's always on the right-hand side of these rectangles? Okay, what's defining? Thank you, Aaron. 5 minus y. Always is over there. What's on the left-hand side always? E to the y, which means we only need one integral to do this with y. Okay? The x way works fine, but this is how it works with y's. But now I need to integrate. I need to tell the rectangles where to start and where to stop. Okay? But it's in y now, not x. So we think, rather than for dx, for x's, we think what's the leftmost, what's the rightmost. For y, we think what's the bottommost, what's the topmost. What's the bottom? Where's my very first rectangle going to be? No. -2. -2. And we're going to go all the way up to the y value at that point. Now, so b is the x value, right? I called b the x value. I need the y value up there now. So when we find that point, when we find the intersection, it spits out a y value. I just didn't pay attention to it because we didn't need it. Now I need it. Okay, so check this. Check out our calculator skills. We find the intersection the same exact way. First curve, second curve, guess. Boom. Now, if I want to store that number, not the x value, the y value, which is currently 1.306556, I'm going to do similar things. I'm going to hit second quit. All right? But I can't just hit store now because what if I hit store alpha A again? Oh my gosh. What? Store alpha A. It's going to spit out the x value. You guys see that? but the y value is being stored. Stop right here, Albano. The y value is being stored, but you got to get it from y1. Because remember, I found where y1 and y2 intersect. So y1 and y2 right now are both saved as that number. So if you want to store it, which you do not have to, you could go into vars, go into y vars, choose one of the functions you found the intersection for, which was y1 or y2, and store that. And I usually let the y values be like c. And that's the y value where they intersect. So it stores the x value as the answer. It stores the y value as y1 or y2, depending on which ones you found the intersection of.
I have a question.
Okay? Yeah.
Why is it that with this one you have to, when you're using it in correct y, you just come back to the right minus the left?
Because you learned this back in like first grade, man. Yo, if you had to do, let's get super simple, 8 and 3, how far apart are they? What do? 8 minus 3, right minus left. What are we really subtracting up here, gang? When I subtract this side minus this side, what are we subtracting? X values or y values? We're subtracting the x values. We're subtracting the x values for a given y value. Okay? That's all we're saying. Which is why we have, this is really x1, and this is really x2. We're doing x1 minus x2. It's just they're changing, so I had to put in the functions that they are with respect to the variable we're integrating with. Okay? Now, we're going to do this in the calculator, and we'd better get the same stupid answer we got when we did it with x's. Otherwise, this doesn't make any sense. Okay? And I'm only showing you this in the calculator because sometimes kids get here and they're like, how do I put y into a calculator? Here's a secret, kids. Your calculator doesn't know what variables on your paper. It just knows it wants to integrate things. It's hungry to integrate. So when you put this into a calculator, you're going to put it in as x. Yeah, you don't need to type in whatever letters on your paper. The calculator always just uses x. So when we do this on a calculator, we're going to hit math 9, -2 to alpha c, because I stored that as that y value, of 5 minus x minus e to the x dx. And it better give me 14.1211. Holy crap, it does. All right. So it gives us the same answer again. It was only one integral. Again, you don't have to do this for this, but this is kind of like a little interesting thing about math. Anytime you have two different ways of solving one problem, okay, sometimes, and this happens later on in a little bit of upper level math, you can trade like a question you're given that's super complicated for a much easier version of that question that has the same answer. Okay. Now, this is a very, like, neither one of these is way simpler than the other. The y version only has one integral, so it's a little bit simpler, but not crazy different. Something, though, that is a little interesting is, if we did this with x and we had to do it by hand, do you guys see this first integral has the integral of ln of x? And we've never learned how to integrate the ln of x. We will last year, but we don't know how to integrate that right now, so we can't do that by hand. But the y version, we can integrate that whole thing by hand. So converting it to a different format makes it easier for us to handle it if we don't have a calculator or something like that. All right. So in general, when we're finding area between curves, you're going to do one of two things. You're going to do the integral from a to b of the top function minus the bottom function dx, or you're going to do the integral from c to d of the right function minus the left function dy. For homework, I put a page from a textbook on Canvas. It asks you to do numbers 1 through 6. It's on the document. I forget. 1 through 6, and it's like 19, 20, and something else, like 17, 18, 19, 20. I don't know. Something like that. Okay? So 1 through 6, ... It says in Canvas what to do. There's 10 of these. I would like you to find the areas. Okay? If you don't have a calculator, use Desmos and graph them and find the intersections that way. Okay? Good talk. Oh, in terms of what we're doing the rest of the week, we will be working on this. I know a lot of kids will not be here Thursday, Friday. Are there a lot of kids not going to be here Thursday and Friday? Band kids? Okay. So tomorrow we're going to work more on this. I might show you something a little slightly new. Thursday we might work as well. I'm giving you spring break work. I know, right? You love that. It's going to be AP review for the AP test, which is very soon. I will give you Friday in class time to work on that if you're here. Okay? Okay.